Thanks for joining us. This is last G-Lab of the semester. We have Surya Raghavendran from Yale and Edinburgh, right now in Edinburgh, to talk about his recent paper on local superconformal algebras. It's a 50-minute talk, but we're going to interrupt with many questions. Okay, thanks, Surya, for agreeing, and go ahead.
Great. Yeah, thanks for the opportunity to speak. It would have been nice to be back in Toronto in person. So I'd like to tell you about some recent work that I did jointly with Fabian Hanner, Ingmar Saberi, and Brian Williams, based on this paper here. And it explores some geometric aspects of superconformal symmetries. Okay. So maybe to set the stage a little bit, let me tell you about a similar story concerning ordinary conformal symmetries. So one thing that we're told in school is that conformal symmetries behave wildly differently in dimension 2 versus higher dimensions. Indeed, in dimension 2, any holomorphic or anti-holomorphic vector field defines a conformal killing vector field. So we find an infinite dimensional Lie algebra. But in dimension above 2, the Lie algebra of conformal killing vector fields is finite dimensional, and it's an indefinite special orthogonal Lie algebra. And this fact is in many ways responsible for maybe the relative niceness of conformal field theory in dimension 2 and the belief that conformal field theories in higher dimensions must be significantly less tractable. But recently, this belief that this kind of dichotomy is a fundamental difference between dimensions, it was revisited by Kapranov. And maybe central to the infinite dimensionality in dimension 2 is a relationship between conformal geometry and complex geometry. And such relations were extended to higher dimensions via the twistor program. And accordingly, Kapranov's approach sort of draws ideas from there. So associated to a complex conformal manifold, one can consider its so-called ambi-twistor space. So the points in this space are complex null geodesics, and it's a complex manifold of dimension 2D minus 3, and it has a holomorphic contact structure. So it was noticed by Lebrun and Mason that this holomorphic contact structure, it knows about the conformal geometry of M. So sections of the sheaf of holomorphic contact vector fields, they recover the Lie algebra of conformal killing vector fields, and at least for d equals 4, H1 is closely related to conformal gravity. So Kapranov in this paper, he sort of rearticulates those kinds of results in the language of derived geometry. Of course, one of the philosophies is that symmetries and deformation should be considered together and define a DG Lie algebra. And Kapranov proposed that one should just look at the DG Lie algebra of derived global sections of this sheaf of holomorphic contact vector fields. And this DG Lie algebra, it sort of reconciles the previous dichotomy that we saw. So the cohomology on affine space, it'll be concentrated in 2 degrees. H0, it's the Lie algebra of conformal killing vector fields, and that's infinite dimensional for d equals 2. And for d equals 2, that's all the all the cohomology. And for d above 2, though H0 is finite dimensional, there's an infinite dimensional H1. Okay. So Kapranov's results establishes some nice uniformity across dimensions to the behavior of conformal symmetries. Okay. So the goal of my talk will be to illustrate a similar picture for superconformal algebras. So these combine conformal symmetries with an extended Poincare symmetries. And the behavior of superconformal algebras across dimensions is even more erratic. So as in the non-super case, they're infinite dimensional in dimension 2 and finite dimensional in dimensions higher than 2. So in dimension 2, these were classified by Katz and van der Loor, and you find, for instance, loop algebras based on finite dimensional simple Lie superalgebras, uh, 3 additional infinite families, and sort of 2 additional entries that don't appear in families. And in dimensions higher than 2, these were classified by Nahm, and you find various finite dimensional simple Lie superalgebras. They occur in infinite families again in dimensions 3, 4, and 6, and there's a single exceptional example in dimension 5, and no examples exist above dimension 6. The existence of these in low dimensions, it basically is in keeping with existence of like exceptional isomorphisms in low dimensions. In each of these cases, the existence of a superconformal algebra basically relies on some exceptional isomorphism. So it's natural to wonder whether there's a similar way as in the non-supersymmetric case to establish some uniformity to this classification, maybe by thinking derivedly a little bit. And Kapranov's approach suggests a kind of course strategy to take. We could try and realize these superconformal algebras as symmetries of some geometric structure, and then try and consider some de Lie algebra that also includes deformations. And just how in the non-supersymmetric case, we're sort of led to a space that naturally features in geometric constructions of conformal field theories, our approach in the superconformal case, it'll sort of naturally make contact with structures that have previously been considered in supergeometric constructions of superconformal field theories. Okay. So that's the motivation. Are there any questions at this point?
Maybe one question. Before the super version, if you just go back to the conformal example, this observation of Kapranov, what impact does it have on physics, do you think?
Right. So you could consider the derived global sections on uh of this vector field of this sheaf of homomorphic contact vector fields on the MB twistor space of AD minus of points, and that'll give you some sort of version of the Witt algebra that should act on sort of any conformal field theory classically. And at the quantum level, conformal anomalies will be encoded by some sort of L infinity extension of that sort of thing. So that hasn't that sort of hasn't been explored, but indeed this sort of thing should act on any higher dimensional conformal field theory. Like one way you might define
So
a
it's
higher
it's more
dimensional
about
conformal field
it's more about giving properties, kind of unexpected properties of conformal field theories in higher dimension. But those higher dimensional conformal field theories, my understanding is that there aren't any real physical examples of them, or is that false?
There are quite a few number of physical examples, I guess. Like I don't know, like you could take you're asking maybe at loop level or something. Yeah, I don't know, maybe like the 3D Ising model at like a critical point or something. That would be an example. Uh, Classically, these things are like ubiquitous. I don't know, like Maxwell theory, self-dual gravity in 4D. Uh,
Okay, I
yeah,
see. Okay,
yeah,
okay, thanks.
yeah. Okay. Cool. Okay. So the main geometric datum that we'll consider will be a certain kind of maximally non-interval distribution similar to a holomorphic contact structure in Kapranov's story. There's this theory of filtered structures due to Tanaka that allows one to translate between certain Lie theoretic and differential geometric data. And they'll sort of allude to that throughout the talk. So given a smooth supermanifold with a distribution, you can define a filtration on each tangent space as follows. So let the kth step of the filtration be spanned by taking at most k-fold brackets of sections of the distribution and then evaluating at p. So the distribution is said to be bracket generating if the filtration is exhaustive. And if not, it'll be convenient to sort of turn it into an exhaustive filtration by appending the full tangent space at the end. Okay. And this filtration doesn't quite yield the structure of a filtered Lie algebra as, to define each step of the filtration, we sort of need to choose an extension of elements of the fiber of this distribution at P to a neighborhood of P. But any two choices of this extension, they'll sort of differ by something of lower filtration degree. So in fact, we have a well-defined graded Lie structure on the associated graded. And the resulting graded Lie algebra, it's called the symbol of my distribution at this point, P. Okay. Now, if I have a Lie superalgebra that's positively graded, I'll say a distribution is regular of type n if the symbol at every point is isomorphic to that Lie superalgebra. Okay. And Tanaka proved that for such distributions, you can sort of characterize the infinitesimal symmetries of the distribution in terms of n via a procedure called Tanaka prolongation, which we'll come back later. Okay. Now, non-integral distributions are actually pretty ubiquitous. I'll maybe list some examples to help build familiarity. So maybe the first example one meets is an almost complex manifold. So there, the distribution is spanned by the anti-holomorphic part of the tangent bundle, and the Lie bracket on the symbol algebra at any point, it's basically defined by the nine-house tensor and its complex conjugate. Okay. Now this symbol algebra, it's still a meaningful notion for an integral distribution, but it'll be abelian. So say I have a complex manifold, then the nine-house tensor, of course, vanishes. And the symbol algebra is the abelian graded Lie algebra given by the complex conjugate of c to the d in degree 1 and c to the d in degree 2. Okay. Now, a sort of mild generalization of the previous example is a manifold with a transversely holomorphic foliation. So there, the symbol algebra is an abelian graded Lie algebra given by a subspace of c to the d such that it plus its complex conjugate spans c to the d in degree 1 and the quotient in degree 2. And then lastly, as I mentioned verbally, if I have a contact manifold, the contact distribution, it's also strongly regular of type given by some Lie algebra, and that Lie algebra here is the Heisenberg Lie algebra. Okay. So the main examples in this talk will be such non-integrable distributions that are based on supertranslation algebras. So for the purpose of this talk, a supertranslation algebra will be a finite dimensional, consistently graded Lie superalgebra supported in weights 1 and 2. So I've chosen some lifts of the Z mod 2 grading on a Lie superalgebra to a Z grading. And I'd like to consider tangential structures that are modeled on these kinds of things. Okay. So say I have a supertranslation algebra and a smooth supermanifold of dimension d/k, where d is the dimension of the odd part. Sorry, there's a typo here. There should be a 2 and there should be a 1. Then a superconformal structure on M of type N will be a regular distribution of type given by my supertranslation algebra. Okay. And the main example of such a thing, which is maybe called the flat model by some authors. So let me consider this simply connected supergroup that exponentiates a supertranslation algebra. And I can define a regular distribution by extending N1 in a right invariant way. Okay. So in terms of global coordinates, which I have on this flat model, the sections spanning D, they recover standard formulae for right invariant supercovariant derivatives that show up in, I don't know, traditional superfield formalisms of supersymmetric field theories. So here, the gammas are structure constants for my supertranslation algebra. Okay. So when people consider sort of superfield formalisms of supersymmetric field theories, they're taking into account this additional sort of geometric structure.
Sorry, can you just go back for a second?
Yeah.
So the DOs are the generators for the distribution. And the distribution, oh, I see. And the distribution is generating this filtration, and then the associated graded has these two components, N1 and N2.
Exactly. Yeah.
I see. So the N2 objects, they come from the failure of the DAs to commute, or they give.
Yep.
Yeah. Okay. Yeah. I see.
Yep. Exactly.
So there's no assumption about the N1. So what you're describing here is a canonical example that exists on any supergroup integrating an algebra that that has these two components. Super translation
Exactly.
group, right? I see.
Yeah. There's nothing about spinors or yeah, like the gammas can just be the structure constant of um, some super Lie algebra in this form.
Okay. All right. Thanks.
Yep. Okay. So I'd like to make the case that it's natural to view manifolds with superconformal structures in the sense that I described as certain DG ringed spaces. Okay. So in the setting of complex geometry, this is perhaps a bit more familiar. Of course, the natural sheaf of functions to consider on a complex manifold is not the sheaf of smooth functions. That doesn't take into account the data of the distribution defining the geometry. The natural class of functions to consider are those that are invariant along the distribution, the holomorphic ones. And there's a resolution that's locally free over smooth functions given by the Dolbeault complex. Okay. But what happens if we have the non-integrable distribution like on an almost complex manifold? So since the distribution is bracket generating, it would appear that asking for functions that are killed by the distribution is not a very interesting thing to do. This is just the complex sheaf, the constant sheaf. So derivedly, the constant sheaf is resolved by the de Rham complex, and the distribution is basically just going to determine some quasi-isomorphic sub of the de Rham complex, right? But it turns out that in many cases, this quasi-isomorphic sub, it has an interesting filtration, much like the Hodge filtration. Okay. And the filtration can be defined as follows. So it's one associated to a positive integer grading on the tangent bundle such that the distribution is a summand. So for instance, for an almost complex structure, we can use the decomposition of the tangent bundle into eigenbundles for the almost complex structure. And that'll induce a grading on forms where the differential decomposes into pieces of non-positive weight as shown. Okay. And so here, the first component, which is the 9-house tensor, it squares to 0. And though the del bar operator doesn't square to 0, it squares to 0 up to mu exact terms. And the cohomology with respect to the first term, that is bigraded, and del bar defines a differential on the totalized degree zero summand. So you can look at the E1 page of the spectral sequence induced by this grading. There's a bigrading there, and the totalized degree zero summand, that's sort of a good version of the Dolbeault complex for an almost complex manifold. Okay. So we'll do the same exact thing in this setting where my non-integrable distribution is given by one of these superconformal structures. Oh, okay. So we can run exactly the same game. There's a natural grading on the de Rham complex that's given by totalizing the homological and internal gradings. And it's easy to see how this works if I choose a left invariant frame. So I'll choose a basis of left invariant forms given as follows. So here, the degrees of lambda a's are, they're of by degree 1 minus 1, and the degrees of the v mu's, they're of by degree 1 minus 2. And we'll consider the grading given by totalizing the sort of internal degree and the homological degree. So again, the totalized grading of these is zeros, so they're exactly like anti-holomorphic forms in the previous example. And the totalized degree of these is -1, so they're like holomorphic forms. Okay? And in this frame, the de Rham differential, it decomposes as follows. And again, this term doesn't square to 0, but this term does. And this term squares to 0 up to terms that are exact for the first term. Okay. So we'll look at cohomology with respect to this first term. It induces a bigrading. The bigrading here gives us a bigrading on this cohomology. And the summand of totalized degree 0 equipped with this term as a differential is a CDJ, which we'll regard as the functions on flat superspace. Okay. So this may seem a little bit ad hoc at this point, though hopefully the parallel with this construction almost complex geometry is makes it seem a little less ad hoc. But it turns out that this CDJ, it sort of already appears in supersymmetric physics, namely in approaches to off-shell constructions of supermultiplets. So I'd maybe like to say something about that. Okay.
In that example, does the d-1 play any role?
That is a good question. Um, yeah, off the top of my head, I don't entirely know what the geometric interpretation of d-1 is. Like, as before, this term is sort of it's like some measure of like superspace torsion, the failure of the integrability of the distribution. But and I'll say something about the geometric meaning of this, but I'm not exactly sure what the meaning of d-1 is off the top of my head. Yeah, thanks.
Sorry, so could you just spell it out again? In the case of the almost complex structure, what is this structure sheaf?
Yeah, right. So we have the de Rham complex with this bigrading. I get a decomposition of the de Rham differential into these kinds of terms. So I look at cohomology with respect to the first term, which squares to 0. And that cohomology is bigraded. And the second piece, which it squared to 0 up to terms that were exact for the first term, it defines a differential, which in particular restricts to a differential on the degree 0 summand with respect to the totalized degree. So I take cohomology with respect to this first term, and then I look at the degree 0 summand with respect to the totalized degree. And I equip that with the differential given by the second summand, and that's a version of the Dolbeault complex for an almost complex manifold.
Okay,
And
so
if
the mu is the degree is the d1, and the del plus mu bar is the d-1.
yeah, exactly. Yeah, or in this case, there are higher degree terms of the differential. So yeah, I think
Oh, so it's -1 and -2.
yeah, exactly. Yeah.
But the del bar has degree 0 in
Yep.
your grading. Yeah, I see.
Yep.
And so
Yeah,
sorry, and you said that you're getting a CDGA,
that's right.
and you're viewing that CDGA as the structure sheaf.
That's right.
Okay, all right, thanks.
Yep. Cool. Okay, so I'd like to tell you about a seemingly different appearance of this kind of structure sheaf, and then I'll sort of tie it all back. Okay. So as I mentioned, this sort of structure sheaf, it appears in off-shell constructions of supermultiplets. So what are the kinds of issues one sees there? So kinematical aspects of supersymmetric field theories turn out to be pretty subtle. So at first approximation, the kind of data you need to specify, at least perturbatively, it's a sheaf of sections of a smooth supervector bundle on spacetime with an action of a super Poincare algebra. But it turns out constructing these kinds of things is quite non-trivial, basically owing itself to the following difficulty. So one thing physicists will say is that supersymmetry often only closes on shell or up to a gauge transformation. So maybe concretely how this might manifest itself in, say, a Lagrangian field theory, where you have an action and you want to show that the action is invariant under some symmetry, you might find some spurious terms whose vanishing requires use of an equation of motion or a gauge transformation, right? And there's a long history of trying to find so-called off-shell formulations of supersymmetric field theories, wherein people add in a bunch of auxiliary fields that maybe nominally have no interesting dynamics, and their transformations under supersymmetries is meant to cancel off some of these spurious terms that you see, right? But we can sort of articulate this defect more precisely homotopically. So say I have a space of fields E and I have a super translation algebra N. So the idea is that I have a Lie map to vector fields on solutions to equations of motion modulo gauge, but it's not induced by any Lie map to just vector fields on E. Okay. However, one thing you might try and do is resolve the equations of motion and gauge symmetries by working in, for instance, the BV-BRST formalism. So if I let E tilde denote my BV-BRST fields, then I have an L infinity map from G to vector fields on E tilde. Okay. So that's maybe a clean way to say things, but an L infinity action poses a lot of challenges. For instance, computing invariants like twists is difficult. So what's a twist? If I have a square zero odd element in my super translation algebra, you can consider the derived invariance of the supersymmetric field theory under the action of the rank 0/1 subalgebra that you get from that odd element. But those invariants can be difficult to compute if you have an L infinity action like this. Okay. Now there's a kind of universal way to try and remedy this drawback, however, that goes under the name of what's called the pure spinor superfield formalism. So names that I should say here like Berkovitz, Satterwall, Nielsen. So the idea is that tilde E, it's a priori maybe a sheaf of complexes of modules that are free over C infinity functions on spacetime. And we should instead sort of fatten this up into a resolution that's free over functions on superspace. And this will have the effect of strictifying this L infinity action because it'll be induced by a spacetime symmetry. And it also solves the above problem about computing invariants like twists because computing invariance under a space-time symmetry is a lot simpler. That's what you might call dimensional reduction. And for instance, if you have a Lagrangian theory, the action functional sort of before and after dimensional reduction, they basically look the same. Okay. The crucial detail, however, is that functions on superspace is not to be understood as C infinity functions. Okay. So let me maybe be a bit more precise. Say I have a manifold. Fields will be sections of the following kind of object. So a differential graded supervector bundle is a z times z mod 2 graded vector bundle, equipped with a square zero differential operator of degree 1 with respect to the z grading. So I'll denote the sort of homological grading with a superscript and the internal grading with a subscript. I may at times want to choose some lift of the z mod 2 grading to a z grading. Okay. So I want to consider symmetries of this kind of thing. So there's a DG Lie algebra given by those endomorphisms that are given by differential operators, and the differential is given by bracketing with this differential. And if I have a super L infinity algebra, a local G module, it'll be a DG super vector bundle together with an L infinity map like this. Okay. So there's a variant of this definition where I might require G to be something like a local super L infinity algebra, but that won't be necessary. And I want to study specific examples where G is a super translation algebra. Okay. So roughly what's meant by a multiplet is a local G module where G is a super translation algebra, but it needs to satisfy some additional compatibility condition. So namely super translation algebras, they'll contain summands that act naturally on space-time, and we want some compatibility with how those summands act on space-time and how they act on fields. Okay. So I'll say that a DG supervector bundle on a vector space is affine if the total space carries an action of the affine Lie algebra such that the bundle projection is equivariant. And say I have a super L infinity algebra equipped with an ordinary Lie map from the Lie algebra of affine symmetries. A multiplet will be a local G module such that the linear part of my L infinity map, when I restrict it along this Lie map, it agrees with the affine structure. Okay. So in particular, the action of affine symmetries on fields is always strict. Okay.
Sorry, can you go back?
Yep.
So this is the definition of what it means for I see.
Yeah,
So here
it's
you're kind of separating the. This is supposed to be like part of the Poincare algebra, the affine transfer. I mean, the Poincare algebra would be a subalgebra of F(x), right?
yeah,
And,
exactly. That's right.
and you're saying
Yeah.
that instead of considering the Lie algebra as a whole, you're separating somehow the part that's coming from the actual manifold, the base manifold.
That's right. That's right. Yeah, I want some compatibility between like how the symmetries of the base manifold act on the base manifold and like on the space of fields. And in particular, I want to force sort of that part of the Lie algebra to act in a strict way.
But for example, if you're thinking of suppose you're thinking of two-dimensional field theories, what would X be? Is X supposed to be R2 or?
Yeah, X would just be R2 then.
I'm just curious why you're going to this case where the space-time is a vector space or an affine space.
Typically, supersymmetric field theories, if you mean like field theories with a action of the super translation algebra, they only exist on flat space unless you do some maneuver like a twist. Yeah.
I see. So in the classification that you were referring to in your motivation, all of those were on kind of Rn.
Those were just statements about classifications of yeah, that was just a statement about classification of super Lie algebras. But so when I
Sorry,
recovered those,
let me make my question more precise. So if the whole point of this is that we're studying things like superconformal symmetries or field theories with superconformal symmetry, then the whole point of it is that they should exist on spaces other than Rn, right? Because they have superconformal symmetry.
absolutely.
But I guess you're just trying to define the models. You're defining what the models are that these theories will be based on, or?
So to get back the super Lie algebras in the classification from the kind of geometric structure, from the kind of DG Lie algebra that I'll introduce, you'll need to consider the DG Lie algebra on flat space. And the point is that this DG Lie algebra, it's sort of like what maybe you should mean by a superconformal field theory is not something with an action of the superconformal algebra, but with an action of this like local DG Lie algebra, which sort of makes sense on like the site of superconformal structures or something.
I see. I see. So these things that you're defining now, I should think that they will be glued together to form your actual space of fields over your base manifold.
Yeah, yeah. Yeah, that's you would get something that's different from maybe what people typically mean by multiplets, but they would sort of be the right notion in that yeah yeah
Okay, thanks.
this is sort of just meant to codify what people in the literature might mean by multiplets. Yeah, yeah, great. Okay. So I want to describe a way to construct multiplets on which supersymmetry will sort of naturally act in a strict way. So the central object will be a space called the nilpotence variety, which I'll describe. So a super Poincare algebra takes the following form. I'm going to choose a lift of the Z2 grading to a Z grading. So the odd piece is some number of copies of spin representation. The even piece, I'm going to complexify things throughout. It'll look like c to the d. And then in degree 0, I'll consider the automorphisms of this kind of data, which will look like SOD, direct some other Lie algebra, which is Lie algebra of R symmetries. And if I choose bases like so, then I get structure constants, which are the gamma matrices. And what is the nilpotence variety? It's just the space of square zero odd elements. Okay. So if you'd like, you could think about this as a sort of moduli of twists of a theory that has G symmetry. And it's sort of, you should sort of think that any invariance attached to a supersymmetric field theory, it actually sort of lives in and families over this cone. And the first hallmark of things like dualities is usually some outer automorphism of the supertranslation algebra, and you should think that statements of dualities are sort of equipping that sort of family over this affine cone with some sort of equivariant structure. Okay. So let me fix some notation. So if R is functions on the odd part, viewed as, I'm just viewing this as a vector space in degree 0, then functions on this affine cone, it's R mod this ideal given by quadratic relations like this. And in terms of the space, I'll describe a functor which, given a G0 equivariant module over R mod I, will produce a multiplet in the sense that I described previously. Okay. So how does this go? So let n be this flat model from before. So there are actions given by left and right multiplication on n. So given a G0 equivariant R mod I module, I can tensor over C with C infinity functions on n and consider the following differential, which is given by right multiplication by these elements Q of A. So explicitly, that takes the following form, which is hopefully familiar from before. Oh. And so this construction, given a G0 equivariant R mod I module, will give me a multiplet. And it has a lot of nice properties. So one of them, if I hand you a square zero supercharge, you can consider the DG super Lie algebra that's just G together with a differential that's bracketing by Q. And let's maybe look at its cohomology. And you can consider the pure spinor functor, but now using GQ and its nilpotence variety as input. Okay. And it turns out that doing that, the kinds of multiplets that I get are the same as what I would get by twisting the multiplet. Okay, so there's a commuting square. So I could twist the multiplet by adding bracketing by Q to this differential here, and I would get a multiplet that has GQ symmetry. But I could also imagine sort of a version of the same functor, but where I use the nilpotence variety for GQ instead. And there's a commuting square like this. Okay.
Can I just ask for you to clarify something really simple? So,
Sure.
Mod G0, the domain of this functor mod G0 over R mod I, right? Here you're using the fact that N1 is a G0 representation. So G0 is acting on N1, and inside N1
That's
you have
right.
this cone of nilpotent the nilpotence cone. And what you're considering for these mod G0 R mod I, these are equivariant vector bundles, G0 equivariant vector bundles over N1.
Yeah, exactly. Over this cone.
Uh-huh. So you're thinking of the cone as an algebraic variety, and you want an equivariant sheaf or an equivariant bundle over that variety.
Yep, exactly. And starting with an equivariant sheaf of modules, I'll produce this functor produces a multiplet.
Uh-huh. So this is, I see. This is like the standard orbit method in a way for producing representations. It's is it some kind of induced representation, or
Maybe. So
oh, maybe that's what you're saying at the end here. The structure sheaf can be, the pure spinor functor can be written as a tensor product. What do you mean by a dot in the last property?
so a dot was the structure sheaf of superspace that was previously defined, which here agrees with this thing. There's a perspective on this which makes it seem very similar to sort of canon results in geometric representation theory, like maybe like valence and Bernstein localization.
Okay.
So a
Okay.
multiplet,
Okay.
it's something like a D module on a homogeneous space. And this functions on this cone. I can write down a complex whose or a CDGA whose H0 is functions on that cone, namely just like Lie algebra cochains on the super translation algebra. So if I have a module over this thing, you can sort of causal dually view that maybe as a module over as something in here. And from here, I'm producing something like a D module on a homogeneous space. So
I see.
this definitely seems very similar to some like
Okay.
canon constructions in geometric representation theory, but I don't have too many sharp things to say other than like cosmetic similarities.
Okay. Thanks.
Yeah. Okay. And yeah, if there's a sort of derived version of this category given by sort of G0 equivariant modules for just Lie algebra cochains on N, and it turns out that this thing is equivalent to all G multiplets. But sort of most examples of multiplets from physics, they'll sort of only come from sort of strict modules for Chevalier-Islander cochains. Okay. And there's also a way to relate the kinds of multiplets that you get from the essential image of this functor to sort of traditional component field descriptions of supersymmetric field theories. So anything in the essential image will come with a filtration that gives theta degree 1. And the E1 page of that spectral sequence, it has a very concrete description in terms of the causal homology of this module gamma. And it'll look very this sort of recovers the traditional component field presentations of supersymmetric field theories. But okay, so to tie it back to what I began this talk with, the structure sheaf of superspace, it's what you get by applying this functor to just R mod I. Okay. Then you can rewrite the pure spinor functor as tensoring over R mod I with a bullet. And you see that it produces things that are like free over a bullet. Okay.
Sorry, so when in that last comment, you mean that if we apply the structure sheaf, if we apply this A R mod I to the structure sheaf of to R mod I itself, then you regain this W with the D bar operator.
Exactly. Yeah, you get yeah, applied to R mod I, you get the degree zero piece of W, where degree meant
The degree zero piece of W.
totalized grading.
Yeah,
Yeah,
thank you.
exactly. Yeah.
Right.
Yeah. And to get the higher degree pieces, you apply a bullet R mod I to sort of the higher degree Lie algebra cohomology of the supertranslation algebra, which is maybe not surprising because like Lie algebra cohomology, that's or the Chevalier-Einberg cochains is the invariant forms on N, on capital N. Okay. Okay, so I had this notion of a superconformal structure. I produced a kind of DG ringed space from that, and I argued that that DG ringed space, it sort of has been studied from some other perspectives in physics. And so from that DG ringed space, I want to produce something that sort of connects back to these superconformal algebras that I began the talk with, right? So I have this DG ring space, and the thing that we want to study is its tangent sheaf. So there's a local DG Lie algebra given by derivations of CDGA. And in the remainder of the talk, I'll sort of tell you a bunch of different ways to think about this object. Okay. So one nice way to think about it sort of uses this pure spinor functor that I described. So there's a sheaf on the nilpotence variety, which you might call the sheaf of surviving translations. So the stock at Q is like, how to say, if you were to consider a twist of a theory with n supersymmetry, then certain translations would act non-trivially, and the stock is exactly those translations. Okay, the stock at a given twist. So that describes some sheaf on the nilpotence variety, and conf n, it's exactly the image of that sheaf under this pure spinor functor. Okay. Okay. So one question you might ask about conf n is what do, or maybe about superconformal structures more generally, in the sense that I described earlier, what do they have to do with conformal structures? Like there's a nice definition of a conformal structure in terms of data like a metric. You would hope that associated to a superconformal structure, there's something like its even part, and I could compare that even part to this definition in terms of a metric. So let me try and motivate that kind of thing. So there's two local DG Lie algebras that you can associate to ordinary conformal structures. Let me describe the first of them, which is maybe the first thing you would think to write down. So it's concentrated in 2 degrees, in degrees 0 and 1. So in degree 0, I have vector fields and smooth functions, and in degree 1, I have symmetric 2 tensors. The top arrow, it's given by Lie derivative of a fixed metric, and I'm going to instead think about the inverse metric just for some ease of some formulae that I'll write later. And the second map, it's just by rescaling G. Okay. And you can compute what H0 and H1 of this thing are, and it's easy to see that in H0 you find exactly conformal killing vector fields, and in H1 you find deformations of the conformal class of my fixed inverse metric. Okay. Another way you could think of a conformal structure is as a reduction of structure group from GLN to ON times the positive reals. Okay. And it turns out that sort of this notion of a conformal structure will be sort of more closely related to Manon's notion of a superconformal structure. This is sort of related to, if you look at supergravity literature, there are formulations of supergravity using sort of variants of Cartan geometry, but there's not really a formulation where the degrees of freedom are some like super analog of a metric. Okay. So there's another local DG Lie algebra that we can define, which governs symmetries and deformations of frames. So say I have a manifold with a framing E by a vector space of E, so an isomorphism between the trivial E bundle and the tangent bundle. And let me fix a Lie algebra that has a map to GLV. Then there's another two-term DG Lie algebra that I can write down that has this form here. And a similar computation of H0 and H1 tells you that this local DG Lie algebra, it governs deformations of this background frame E, but considered up to coordinate transformations that are induced by the reduction of structure from GLN to M. Okay. Now, it turns out that these two ways of describing deformations of ordinary conformal structures are equivalent. So say I have an inner product on V dual. This determines a subalgebra of GLV, which is isomorphic to SOV, direct some GL1. And there's an explicit L infinity map that gives me an equivalence between the first model for conformal structures that I described in terms of metrics and frames for SOV direct some GL1. Okay. So here rho is the part of this degree 0 field that is valued in SOV, and lambda is sort of the scale part. Okay. Now it turns out that even superconformal structures are closely related to conformal structures in the following sense. So conf n has a bigrading given by weights and theta degree, okay? And conf n it's a super Lie algebra, and the parity as a super Lie algebra, it's determined by the difference of internal homological degree and theta degree considered mod 2, okay? So let's consider the sub-DG Lie algebra consisting of elements of even parity. And so it turns out that the elements of that sub of strictly positive totalized degree is an ideal. And moreover, if I have a super translation algebra for which the odd bracket is surjective, and let G0 denote the degree 0 derivations of the super translation algebra as I've been doing, then the DG Lie algebra controlling deformations of G0 frames, it's quasi-isomorphic to a sub of conf n plus modulo this ideal, okay? So in particular, under some additional assumptions, namely that this bracket map is surjective and the image of the projection from derivations of n to derivations of the even parts is SOD directs in GL1, you get a map from conf n to deformations of conformal structure using this sort of metric data. So the point is that a superconformal structure in the sense of Manin, it always sort of affects a reduction of structure group of the underlying manifold to the degree 0 derivations of your, to some group exponentiating the degree 0 derivations of your super translation algebra. And if I make some additional assumptions on what that looks like, then that reduction of structure is such that you actually get an ordinary conformal structure, okay? So that's the sense in which these two notions are related. Okay. Maybe I'll pause for questions briefly. We're good. Okay.
I think we're good. We're good. Yeah.
Great. Okay. So let me tell you how H0 of conf n recovers superconformal algebras now. And unfortunately, this result, it's not like the most like conceptual thing. It's sort of just we recover some classification result by like stringing together some other classification results or something. So what's the idea? So let me fix the super translation algebra. So I can look at the global sections of conf n, and you get this this Lie algebra that's called the maxitive transitive prolongation of n. So it's sort of the unique way of extending n to like an infinitely graded, an infinite dimension, a possibly infinite dimensional Lie superalgebra, or the same. The super translation algebra was supported in finitely many degrees and it had finite depth. So you can ask if you can extend it to something that is supported in as many degrees as possible, satisfying some additional conditions, and that's what this maximal transitive prolongation is. Okay. And so there are some results of Altomani and Santi, and a follow-up paper by Santi and Dennis that tells you that the symmetries of a superconformal structure on a flat model are isomorphic to the maximal transitive prolongation of n. So that's what's used in the first bullet point here. And then there's a separate classification of these sorts of maximal transitive prolongations of supertranslation algebras. And when a superconformal algebra exists, the maximal transitive prolongation, it's isomorphic to that superconformal algebra. And in other cases, the maximal transitive prolongation, it basically just extends the super Poincare algebra by scale transformations. Okay. So that's the sense in which on flat space, this thing which you can associate to sort of any superconformal structure recovers superconformal algebras.
Sorry, I didn't really understand the previous slide, but can I just ask something about it? So, in all of the examples that you were speaking of, where you had like from physics, from NAM and so on, where you had these superconformal symmetries, those were all not fully defined, right? They're not. We're talking about off-shell superconformal symmetry, and in those cases they were not fully defined off-shell. Is that right? And this is saying something about the L infinity enhancement of all of those cases, or?
So in let me see. So this is producing a right. Okay, so there's so conf n, it's some sheaf of DG Lie algebras that exists maybe on the site of superconformal structures. And the statement is that you can evaluate it on this flat model, and then H0 will either look like just a super Poincare algebra, direct sum GL1, if n is chosen to be like the same amount of supersymmetry as something in or sorry, not chosen to be the same amount of supersymmetry as something in Non's classification. And if n is chosen to be the same amount of supersymmetry as something in Non's classification, then H0 turns out to be bigger and it gives you something in Non's classification. Did that speak to your question at all?
I guess what I'm wondering is that my understanding is that what you're the previous, the talk up till now, it establishes the right technology for speaking about these superconformal symmetries
Right.
in this kind of in this kind of L infinity enhanced way that was not available to physicists previously, who spoke about there being on-shell supersymmetry, right? So if you want to speak about off-shell supersymmetry, you're saying this is the technology that we should use. So now my question is, in those other models which were claimed to be superconformal, is it actually true that they are all L infinity superconformal in the proper sense? You can try to correct my question if it makes no sense.
Those those are honest super Lie algebras that exist, and like as Lie algebras. And then if I hand you some model that's supposed to be a superconformal field theory,
Yes. Like, let's say
you
if we
can
take the
ask.
two-dimensional the one I
Right.
love most is the 2, 2, supposedly superconformal algebra that it only exists on shell. So I think I understand what was wrong with my question. I was asking about Nam's classification. He was only classifying the superconformal algebras, but I'm talking about the multiplets and the actual field theories uh,
Right.
that are believed to be superconformal. Yeah.
So right. So yeah, let me say maybe what this remedies and maybe how physicists would have talked about superconformal field theories. So they would say like the superconformal field theory exists on flat space, full stop. Maybe it's a question about whether maybe there's a question about like whether the relevant superconformal algebra 2D n equals 2 comma 2 say acts in a Lie way or an L infinity way. So now what this perspective buys you is, say you have a superconformal structure that of type the 2D n equals 2 comma 2 super translation algebra, then you can take this sheaf of DG Lie algebras and you can evaluate it on that superconformal structure, and that thing will act. If it's not the flat model, it's not going to recover the exact super Lie algebra that's in the classification of Katz-Van der Loor, say, for the two-dimensional case. But a priori, physicists would say like that theory is just not a superconformal theory. It doesn't have any nice symmetries or something. Though they may say you could couple the theory to a rigid supergravity background. So this is sort of reinterpreting this thing about coupling to a supergravity background as the action of a different DG Lie algebra, as the action of some other Lie algebra. Does that help at all?
Yeah. Okay. Thank you.
Okay. Okay, so this has been a lot of formalism, and so I said before the talk that a lot of the paper is basically just examples. So I wanted to sort of front load the formalism in the context. But there's one example which I think is really cool, and personally was one of my motivations for pursuing this project. So I just want to maybe end on that example. So this example is related to these sorts of nebulous 60 n equals 2 comma 0 superconformal field theories. Okay. So the 60 n equals 2 comma 0 super translation algebra, it looks as follows. So using the isomorphism between spin 6 and SL4 after complexifying, the spin rep, the positive chirality spin rep is the fundamental of C4, or of SL4. And I have n equals 2 comma 0 super symmetry. So I take 4 copies of that. And the complexified translations, of course, are just C6. And the odd bracket, you use a symplectic form on C4, and this spin 6 equivariant isomorphism. Okay. And if I view, and sorry, there's a typo here. This should be a 4. If I view an odd element as defining a map like this, then it's easy to see that any such map of rank 1 will be a square 0 supercharge. Okay. So I can take such a thing and I can look at the twist. Okay. So I twist, so I add bracketing with Q to the differential. I consider a differential that's given by bracketing with Q, and I take cohomology. And the result is the following Lie algebra. So in degree 1, I have C3 tensor C2. The C3 well, yeah, this C2 is sort of yeah, the tensor factors sort of line up. Yeah, and in even degrees, I just have a copy of wedge 2 C3. And the bracket from here to here, it's just given by the wedge product and symplectic contraction once again. Okay. So I can look at conf of NQ. So I look at the TG Lie algebra that's describing deformations of a superconformal structure of type NQ, but just on flat space. Okay. And I can look at the corresponding component field multiplet. So there was this filtration by theta degree, and which I mentioned the spectral sequence associated with that filtration. It sort of recovers sort of traditional component field formulations of supersymmetry. So I look at that component field multiplet associated to conf NQ. I can look at its I can consider it formally on a formal 3 disk, and you find a strict Lie algebra which is isomorphic to an infinite dimensional exceptional simple Lie superalgebra in Katz's classification called E36. So previously we had found this thing appearing in the context of 11-dimensional supergravity as a sort of asymptotic symmetry on a twisted version of ADS7 times S4. And here we find it as sort of uniformizing the moduli of superconformal structures that are based on NQ here. Okay, so this gives a geometric interpretation of one of the 5 exceptional things in Katz's classification of these infinite dimensional simple Lie superalgebras. Okay, that's all I wanted to say. Thanks.
Okay, great. Thank you.